Hello. So, in the last class we started discussing about convex functions. So, we defined convex functions and then started studying about the properties of the convex functions and how to characterize convex functions. So, let us recall the definition of a convex function. So, if we are given a function, so we are taking a function f from R to R in this case, and suppose we take any 2 points on the real line, let us call them as A and B, and so the corresponding points on the functions are A f A and B f B. Now, if you take a chord joining these 2 points, so in the case of convex functions, this chord always lies on or above the function, or in other words, suppose if we interpolate the points on this line segment joining A f A and B f B. So, for every point we will get a x coordinate and the y coordinate. Now, the y coordinate of that any point on this line segment is always has a value which is always greater than or equal to the value of the function at that point. So, if you take a point C, suppose here, so the value of the function at C is C comma f c, right, and then if we take this point, the corresponding point on this chord, and if you find out its y coordinate, now that y coordinate will always be greater than or equal to f c. So, if that happens for any A and B in the domain of the function, then we call it as a convex function, or in other words, if you take a chord joining any 2 points on the function, the chord always lies on or above the function. And then we also saw some properties and characterizations of convex functions, and one of the important characterizations of convex functions is the epigraph. So, epigraph of a convex function is a convex set, and we proved that if the epigraph of a function is convex, the function is convex, or if the function is convex, then the epigraph of the function is convex. Now, in today's class, we will see more properties of convex functions, especially when the functions are continuously differentiable or twice continuously differentiable. We also will see some ways to derive more convex functions than using the existing convex functions, and we will also see how to extend the definition of convex functions. We have defined convex functions using only 2 points, say x1 and x2 in the domain. So, f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2, where lambda is in the range 0 closed interval 0 to 1, and x1 and x2 are from the convex domain set. So, can we extend it to multiple number of points? We will see these properties in today's class. Now, in the last class, we talked about the level set. So, the level set of any function f is defined as the set of all points x in the set C, such that f of x less than or equal to alpha, right, where alpha is a real number, and we call this as a set C alpha because there is a parameter alpha associated with the set. Now, if f is a convex function, then we showed that the level set C alpha is a convex set for any alpha. Okay. So, we will see some of the interesting properties related to this. Now, so what we have seen is that if the function is convex, then the level set of the function is convex. So, suppose let us take a function h x, let us take a function h x where h is a convex function, and let us take the set h x less than or equal to 0, and we have h is a convex function. Now, if you consider the set of all points x such that x in the domain of H such that Hx is less than or equal to 0, then by the definition of level set, by the properties of convex functions, Hx less than or equal to 0, set of all x such that Hx less than or equal to 0 is a convex set if H is a convex function. Now, we can take different convex functions. So, let us call them as Hj, where each Hj is a convex function. So, each Hjx set of all x such that Hjx less than or equal to 0 is a convex set. And now, what we are going to do is that we are taking the intersection of all these convex sets. So, as we have studied in earlier classes, the intersection of convex sets is a convex sets. So, the set of all x such that Hjx less than or equal to 0, Hj is a convex function, is a convex set. So, let us assume that j are going from 1 to m. So, we have m convex functions, and then we are considering the set of points such that Hx less than or equal to 0 for all j going from 1 to m. Now, this will form a convex set. Now, in addition to this, suppose we have set of equalities. So, let us call them that Ex equal to 0 is another type of set. Now, so if suppose let us just consider the set of the type x. So, x belong to the domain such that Ex equal to 0. Now, this set will be a convex set if and only if your Ex is of the type A transpose x plus b. So, in other words, so the sets of all points x such that Ex equal to 0 is convex if and only if Ex is affine. Now, let us take some certain number of such affine sets. So, let us assume that each Ei is of the type Ai transpose x plus Bi, where Ai's are not equal to 0 and I is going from 1 to L. Now, so we have Hx less than or equal to 0, where Hj is a convex function, and we have m such convex functions. So, this set is a convex set. So, in addition we have some more sets, some more functions Eix which are affine of the type Ai transpose x plus Bi, and this also forms a convex set. So, we have a collection of convex sets and their intersection. So, each Hx less than or equal to 0 is convex set, Ex equal to 0 is convex set, and we have intersection of this convex sets. Now, we know that any intersection of any collection of convex sets is a convex set. Right. So, let us consider a problem where we want to minimize a function f of x subject to the constraint that Hjx less than or equal to 0 and Eix equal to 0, where each Hj is a convex function and Ei's are affine function. Now, let us assume that f is also a convex function. Then this problem that we have got, this is a convex programming problem. So, this problem is convex programming . And we have seen that for a convex programming problem, every local minimum is a global minimum, and all global minima form a convex set. So, a typical convex programming problem can be written in the form minimize fx subject to the constraint Hx less than or equal to 0, where Hj is a convex function, f is a convex function, and Eix equal to 0, where Eix is of the type Ai transpose x plus Bi, I going from 1 to L. So, this is a typical convex programming problem. Now let us look at some of the examples of convex programming problems. Now, the first example that we can think of is a very simple example. Suppose we consider the problem minimize C transpose x subject to A x less than or equal to b. Now, the objective function here is a linear function, and we know that any linear function is a convex function. Now, the constraint set, we have seen that this constraint set is a convex set. So, this is a convex programming problem. Now, if you want to see the example of one such problem, so suppose this is our set of all x such that A x less than or equal to b. So, this is our constraint set, and suppose our function that we want to minimize is an affine function. So, the normal to that hyperplane is pointing in this direction. So, this is the function C transpose x. Now, this affine function we want to or this linear function we want to minimize. Now, you will see that if we want to minimize this function, the minimum probably would occur at this point. If this is our affine function. Now, if we change the affine function, so you will see that this is the only minimum for this. If our objective function is C transpose x, where C is a vector in this direction. Now, suppose if we change the vector C. So, suppose if we make the vector C to be like this, then if you want to minimize this function, so you will see that again this will be the minimum. So, let us change the vector C again. Now, so if we take this as our C vector, and if you try to minimize, you will see that this entire line segment joining these 2 points forms a solution set for this problem. We will see more about such kinds of problems later in the course, but geometrically one can be convinced that this entire line segment joining the points. So, let us call these points as P and Q. So, the entire line segment forms a solution set for this problem if C chosen to be like this. So, you will see that the solutions, there are multiple solutions in this case, but they form a convex set. So, as we studied in the last class that this is a convex programming problem. So, every local minimum is a global minimum. So, all these are global minima. At these points we get the same objective function value, and in addition to that, all these solutions which are on the line segment P and Q, they form a convex set. Now, let us see some more examples. So, let us consider the problem minimize half of x transpose h x minus C transpose x subject to the constraint that A x less than or equal to b, where h is a symmetric positive definite matrix. Now, if H is a symmetric positive definite matrix, then one can see that one can show that this is a convex function. We will see that in today's class, but if under those circumstances and the constraint set of the type Ax less than or equal to b, this is going to be a convex programming problem, which is again has the same properties as that of any typical convex programming problem. So, let us see one more example. So, let us consider minimize x1 plus x2 subject to the constraint that x1 square plus x2 square less than or equal to 1. Now, if we take this constraint set, now it is a circle with center 0 and radius 1. So, this is going to be our constraint set, where our x1 is this coordinate and x2 is this coordinate, and x1 plus x2 is a x1 plus x2 equal to constant is a line in this 2-dimensional space, and what we are trying to do is that we are trying to minimize this the value of this objective function x1 plus x2 subject to the constraint that x1 square plus x2 square less than or equal to 1. Now, you will see that this is an affine function, so it is a convex function. Now, the constraint set you will see that it is also a convex set, the points on the boundary as well as the interior of the circle. So, the constraints are convex set. So, this is a nice convex programming problem, and you will see that the minimum of this function lies at some point somewhere here. Okay. So, this function has a unique. So, this is going to be our global minimum. So, the x1 and x2 coordinates at this point will tell us about the global minimum, and if we plug in those values of x1 and x2 in this objective function, then we will get the optimal objective function value. So, these are some examples of convex functions and convex programming problem, and you will be convinced that the global any local minimum of a convex function is a convex set, is a global minimum, and all these global minima form a convex set. Now, if we look at the definition of a level set, we just say that the set of all x such that f x less than or equal to alpha. So, this was the definition of a level set, and so if we so what we have seen is that f is a convex function, then the level set C alpha is a convex set. Now, the converse of this statement is not true. For example, if we consider a function f x equal to x cube, and that function would look like this. Now, if you take this function, the level set of this function, you can check that that is a convex set, but this function is not convex. So, if f is a convex function, then the level set of that function, all the level sets of that function are convex, but the converse is not necessarily true. Now, so far we have studied some properties of convex functions without assuming any differentiability or twice differentiability. Now, we will see some properties related to the differentiable or twice differentiable convex functions. Now, the first theorem that we are going to see now is that assumes that f is a differentiable function. So, let us consider C to be a convex set, and f is a function, differentiable function defined on the set C, and the function is real valued. So, let us denote the gradient of the function by g x. So, throughout this course, we will use g x to denote the gradient of the function f x, and if f is a function from R to R, the g x will be a scalar, that will be the derivative. Now, the theorem states that if f the function f is convex if and only if if you take any x1, x2 in the domain of that function and x1 is not equal to x2, then f of x2 greater than or equal to f of x1 plus gx1 transpose x2 minus x1, and that happens for all x1 and x2 belongs to C. And further, the function is strictly convex if this inequality holds strictly for all x1 not equal to x2. Okay. Now, before we study the proof of this theorem and its the implications of this theorem, so let us try to see the geometrical interpretation of this theorem. So, let us take a function f x which is shown here with the green line, and so what the theorem says is that this function is convex if and only if. So, if you take the right hand side of this inequality, the right hand side of this inequality says that so f of x1 plus gx1 transpose x2 minus x1 indicates the affine approximation of the function at x1. So, if we take a point x1 and take an affine approximation of the function shown by a magenta line here, the dotted dashed magenta line. So, this is an affine approximation of the function f at x1. Now, this affine approximation if we use and then find the value of the function at x2. So, this is the value of the function at x2. So, f of x2 is always greater than or equal to the corresponding value on this affine approximation at this point x2. Okay. So, in other words, the affine approximation of a convex function does not overestimate the function. So, this line is always on or below. So, this line which we the affine approximation that we have taken here, that always lies on or below the function. Now, this theorem is very important to characterize convex functions. So, remember that the function is convex if and only if this holds. So, if this holds, then we can definitely say that the function is convex. We will study some other implications of this theorem later. So, let us first prove this theorem. Now, the proof is in two parts. So, the first part assumes that the function is convex and we prove that the inequality holds, and in the other part we will do the we will assume that the function is not convex and we will show that the inequality does not hold. Okay. So, let us start proving the first part. So, let us assume that the function is convex. Now, we can use the definition of a convex function. So, we take any x1, x2 in the domain, then f of lambda x2 plus 1 minus lambda x1 is less than or equal to lambda f of x2 plus 1 minus lambda f of x1 for all lambda in the range in the closed interval 0 to 1. So, this is by the definition of convex functions. Now, let us rearrange the terms here. So, let us take the x1 term and separate it from lambda into x2 minus x1, and similarly we can do the rearrangement on the right side. Now, what we can do is that we can bring this f of x1 on the left side and divide the whole expression by lambda, assuming that lambda is not equal to 0. So, we can do this and write f of x1 plus lambda into x2 minus x1 minus f of x1 divided by lambda less than or equal to f of x2 minus f of x1. Now, if you take so remember that lambda is not 0, but lambda is in the open close interval 0 to 1. Now, if we take the limit as lambda tends to 0, then this denotes the directional derivative of f at x1 along the direction x2 minus x1. So, this the letting lambda tend to 0 where lambda is a positive number. So, what we get is g of x1 transpose x2 minus x1, that is the directional derivative of f at x1 defined along the direction x2 minus x1. Now, that will be less than or equal to f of x2 minus f of x1, and this shows that f of x2 will be greater than or equal to f of x1 plus gx1 transpose x2 minus x1. So, this is the inequality that we wanted to show. So, if f is convex, using the convexity of f, we can show that this inequality holds for a differentiable convex function. Now, let us look at the other part of the proof. So, let us assume that f of x2, let us assume that the inequality holds, and then we show that the function is convex. So, let us take this inequality that we have in the theorem, and that holds for any x1, x2 belong to C. Now, since it holds for any x1, x2 belong to C and C is a convex set, we can take any x in the convex set C, which is the combination of x1 and x2, and then rewrite this equality in terms of the different points. So, suppose we take any x which is a convex combination of x1 and x2, then we can say that the inequality holds for x1 and x. So, f of x1 is greater than or equal to f of x plus gx transpose x1 minus x. And similarly, we can say that the inequality holds for x2 and x, because x2 and x are again two different points in the set C. Now, we have to show that the function is convex. So, what we have to show is that lambda f of x1 plus 1 minus lambda f of x2 is greater than or equal to f of lambda x1 plus 1 minus lambda x2. Now, if you look at x is nothing but lambda x1 plus 1 minus lambda x2, and what we want is to show that f of x is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. So, what we do is that we multiply the first inequality by lambda and the second inequality by 1 minus lambda. Remember that lambdas are positive. So, the inequalities will remain as they are, and what we get by multiplying the first expression by lambda and the second expression by 1 minus lambda is lambda f of x1 plus 1 minus lambda f of x2, and that is greater than or equal to f of. So, lambda f of x plus 1 minus lambda f of x will make it lambda f x, and then lambda gx transpose x1 minus x plus 1 minus lambda gx transpose x2 minus x. Now, we have to rearrange these terms, and if you rearrange these terms, you will see that what we get is f of x plus gx transpose lambda x1 plus 1 minus lambda x2 minus x. Now, if we look at this definition of x is nothing but lambda x1 plus 1 minus lambda x2. So, this x is nothing but lambda x1 plus 1 minus lambda x2. So, this quantity here in this parenthesis vanishes, and because of which what we get is lambda f of x1 plus 1 minus lambda equal to f of x is greater than or equal to f of x, and f of x is nothing but f of lambda x1 plus 1 minus lambda x2. So, you will see that this is the definition of a, this is from the definition of a convex function, f is convex. So, we have shown that if f is convex, then the inequality holds, or if the inequality this inequality holds, then the function f is convex. Now, we will see some of the results related to this. So, one of the most important interpretations of this result, as I mentioned earlier, is that if f is a differentiable convex function on a convex set C, then the first order approximation of f at any x1 belonging to C never overestimates f of x2 for any x2 belonging to C, or in other words, this affine approximation or the first order approximation of f at any x1, it does not, that line does not cut the function at any point of time. It always lies either on the function or below the function. So, it does not overestimate the function, and if a function is strictly convex, then one can say that in those circumstances the first order approximation of a strictly convex function always underestimates f of x2 for any x2 belonging to C. So, this result is important. We will see the some more results related to this. Now, suppose we take a open convex set in the space of real numbers. So, let that set be C, which is a subset of R, and let us define a differentiable convex function f from C to R. Now, so let us consider any 2 points x1 and x2 in the domain of that function such that x1 is less than x2. Now, what we are interested in finding out is that how do the remember that this is now a function on one variable. So, we have, and in addition to that we have chosen 2 points where x1 is less than x2. So, can we say something about the slopes of the functions at these 2 points when the function f is a differentiable convex function? Now, by using the theorem that we have studied so far, we can see that f of x1. So, since x1 and x2 are these 2 points in the domain, f of x1 is greater than or equal to f of x2 plus f dash x2 into x1 minus x2, and similarly f of x2 is greater than or equal to f of x1 plus f dash x1 into x2 minus x1. Now, we are interested in finding out what happens to the slopes of these 2 functions at these 2 points, especially when x1 is less than x2. So, what we will do is that we will write how does f of x2 minus f of x1 look like. So, we can see that f of x2 from this first expression, we can see that f of x2 minus f of x1 is less than or equal to f dash x2 into x2 minus x1, and from the second, f of x2 minus f of x1 is greater than or equal to f dash x1 into x2 minus x1. Remember that x1 is less than x2, so x2 minus x1 is greater than 0. So, if we divide throughout by x2 minus x1, which is a positive number, what we get is that f dash x2 will be greater than or equal to f dash x1 for all x2 greater than x1. So, this means that if we have a differentiable convex function on an open set C, which is a subset of R, and if we choose any 2 points x1 and x2 such that x1 less than x2, then the slope of the, and if f is a differentiable convex function, then the slope of that function at x1 is always less than or equal to the slope of the function at x2. So, which means that the slope of such functions defined on the set C, which is a subset of R, and the function is differentiable. So, the slopes of such functions, differentiable, f is a differentiable convex functions, the slope of such functions are non-decreasing. So, if we have a differentiable convex function of one variable defined on an open interval C, then the derivative of f is non-decreasing. In fact, the converse of this statement is also true, that if you have a function, differentiable function defined on an open interval C, then the if the derivative of f is non-decreasing, then the function is convex. So, this is an important property of convex functions. Now, let us consider a convex programming problem. So, minimize f(x) subject to x belongs to C. Now, since this is a convex programming problem, we have assumed that f is a convex function and C is a convex set. So, only in that case we can call this as a convex programming problem. Now, let us make assumption that f is differentiable. Now, if f is differentiable, suppose we take a point x hat, which is in the domain of that function. Now, by using our theorem, we can say that the optimal objective function value of this convex programming problem, if you want to find out the lower bound on that optimal objective function value, what we can do is that we can take an affine approximation of f at x hat. So, that affine approximation will look like this, f of the affine approximation of f at x hat is f of x hat plus g x hat transpose x minus x hat. Now, if we take this as our new objective function and then solve this problem, now the variable is x. So, the objective function, this first quantity is a constant quantity. So, we can ignore that. So, this is a affine function in X. Now, if we get an optimal value of this problem, now that optimal value gives us a lower bound on the optimal objective function value of the original convex programming problem. So, let us see that using an example. Now, suppose we have a convex function, define it like this, and then suppose we take an affine approximation of f at a particular point. Now, suppose we are interested in finding out the optimum of this function subject to the constraint that the interval that we are looking at is suppose a and b. Okay. Now, our current result says that if we take any point, say let us call this as x1 and take the affine let us call this as x hat. So, the x hat is our current point, and if we take a affine approximation of the, so this is a convex function, and if you take a affine approximation of this, now if we minimize this function, right. So, the minimum value of this affine approximation is at this point. This is an minimum value of the affine approximation over the set closed interval a b. Now, the result that we have seen says that this gives a lower bound on the optimal objective function value. So, this the optimal objective function value, the optimal point of this is our x star, and the optimal objective function value at this point is this, but then we get a lower bound on the optimal objective function value by using an affine approximation of f at x hat. Now, this lower bound may be a crude bound, but nevertheless it gives us some idea about the optimal objective function value. It gives an idea about the bound on the optimal objective function value. Okay. Now, let us look at one more result. Let us again consider a convex programming problem where f is a differentiable convex function and C is an open convex set. Now, let us consider some x star which belongs to the set C such that the gradient of the function vanishes at x star. So, in other words, g of x star is 0. Then what can we say about x star? Now, if we recall our earlier result on a general one dimensional optimization problems, you would have seen that the derivative, when the derivative vanishes, it does not guarantee anything whether that point is a local minimum or not. Now, convex functions have this special property, and we will see what happens to this x star. So, g of x star is 0. So, suppose if we take any x in the set C, then using our theorem we can say that f of x is greater than or equal to f of x star plus g x star transpose x minus x star. Now, we know that g of x star is 0. So, this quantity is 0. So, therefore, we can say that f of x is greater than or equal to f of x star for all x belong to C. Remember that this inequality holds for all x belong to the set C. So, therefore, f of x is greater than or equal to f of x star for all x belongs to C. Now, this means that x star is a global minimum of f over C. So, for convex functions, this condition g of x star equal to 0 is sufficient to ensure that x star is a global minimum of f over C. Remember that we are taking C as an open convex set. So, this is a very important result, and the reason why the second order information is not really important to identify the global minimum of the convex set, that we will study now. So, it turns out that the Hessian matrix in the case of convex functions is always positive semi-definite. So, that is why we really do not have to worry about the second order information to write the sufficient conditions for the global minimum of a convex function. The first order conditions are enough to guarantee that a particular point is the global minimum of f over the open convex set C. So, let us look at the second important theorem where f is a twice differentiable real valued function on an open convex set C, which is a subset of Rn. Now, the theorem says that if then f is convex if and only if its Hessian matrix Hx is positive semi-definite for each x belong to the set C. So, we will prove this theorem. So, again we have to prove this theorem in two parts. So, we will consider the first part. So, let us assume that x1 and x2 belong to the set C and Hx is positive semi-definite for each x belong to C. And what we have to show is that in such a case the Hessian the function f is the Hessian matrix is positive semi-definite for each x belong to C, and therefore, the function has to be convex. Now, to show that the function is convex, we can either show that the basic property of the convexity holds, or we can show that the condition which was shown in the previous theorem that also that holds. So, let us take x equal to lambda x1 plus 1 minus lambda x2, a point on the line segment, open line segment joining x1 and x2. And if we use the truncated Taylor series, we can write the truncated Taylor series at x1 as f of x2 is equal to f of x1 plus gx1 transpose x2 minus x1 plus half x2 minus x1 transpose hx x2 minus x1. Now, remember that Hx is positive semi-definite for each x belong to C. So, this quantity is always non-negative. So, therefore, we can write f of x2 to be greater than or equal to f of x1 plus g of x1 transpose x2 minus x1. And by our earlier theorem, this means that the function f is convex. So, this is the first part of the proof. Now, let us look at the second part of the proof. So, let us assume that H is not positive semi-definite for some x1 belonging to C, and then we come up with the result that if H is not positive semi-definite, then f is not convex. So, if H is not positive definite for some x1, then there exists some x2 in the set C such that x2 minus x1 transpose hx1 into x2 minus x1 is less than 0. Now, we will make use of this fact and to show that f is in such under this assumption f cannot be a convex function. Now, so let us again take a point x which is on the open line segment joining x1 and x2, and then write the Taylor series truncated Taylor series of f at x1. So, f of x2 is nothing but f of x1 plus the term related to the gradient of f at x1, and then the term related to the gradient of f at in any point x which is on the open line segment joining x1 and x2. Now, remember that h of x, this quantity is less than 0, this is by our assumption. Now, f is twice continuously differentiable. So, h is a continuous function. So, we can take x sufficiently close to x1 such that this quantity is the third quantity in this expression is less than 0. Now, if that happens, so if this quantity is less than 0, then the f of x2 will be strictly less than f of x1 plus gx1 transpose x2 minus x1. because this if x is sufficiently close to x1, the last quantity becomes strictly less than 0, and we can write this. And since this is true, certainly f is not convex because of our earlier theorem. So, if we start with the assumption that H is not positive semi-definite, then that implies that f is not convex. So, this means that f is convex if and only if the Hessian matrix at any point in the domain is a semi-definite, a positive semi-definite matrix. Now, we can have one more result which says that f is strictly convex on C if the Hessian matrix Hx of f is positive definite for all x belonging to the set C. Now, the proof of this result goes along similar lines, so we will not prove this. So, remember that f is convex on C if and only if the Hessian matrix of f at any x is positive semi-definite, while f is strictly, if the Hessian matrix is strictly positive definite, then f is convex. Remember that this is not if and only if. So, I leave it as an exercise to find out the case where f is strictly convex, but the Hessian matrix of the function is not positive definite. But if the Hessian matrix is positive definite, then we can definitely say that f is strictly convex. Now, let us see some examples of convex functions. So, let us take a function f defined from Rn to R as f x is equal to half x transpose x plus b transpose x plus c, where A is a symmetric matrix in Rn. Now, if we take the Hessian of this matrix, the Hessian of this Hessian of this function, the Hessian is the matrix A. Now, by our theorem, we have that f is convex if and only if the Hessian matrix is positive semi-definite. So, this function is convex if and only if A is positive semi-definite. So, whenever A is positive semi-definite, this is a quadratic function in x. So, this function is convex. Let us look at another example. Suppose let us take a real valued function defined on the set of positive real numbers. Now, this set of positive real numbers form a convex set, and let us take the function f to be f of x equal to x log x. Now, we want to test whether this function is convex or not. Now, note that this function is twice differentiable. So, we can take the second derivative of this function and see its behavior, and based on that we can conclude whether the function is convex or not. Now, we can take the derivative of this function, and the derivative is 1 plus log x, and the second derivative is 1 by x, and that quantity is greater than 0 for every positive real number or for every x belonging to C. So, therefore, since the second derivative is always greater than 0, we can say that f is convex. In fact, one can also say that this is a strictly convex function because second derivative is always greater than 0. Now, let us take a function f x equal to half norm x minus b square. Remember that we use two norm suppose, and we can rewrite this function as half of x minus b transpose x minus b, and if you take the gradient of this function, if you take the Hessian of this function is A transpose A, and A transpose A, this matrix is always positive semi-definite. So, this function is always a convex function. The function f is always a convex function. Let us consider a function f of log x defined again on the set of positive real numbers. Now, if you again take the first derivative and the second derivative, So, the first derivative is 1 by x and the second derivative is minus 1 by x square, and that quantity is always less than 0 whenever x belongs to C. So, one can say that if that happens, then the function is concave. So, these are some examples of convex functions. One can also define new convex functions using existing convex functions. We will study later. Now, let us look at an important inequality called Jensens inequality. Now, let f be a real valued function defined on a convex set C, which is a subset of Rn. Then f is convex if and only if f of sigma lambda xi is less than or equal to sigma lambda I f of xi. So, this is a Jensens inequality where x1 and x1 to xk, they are from the set C, and lambda i's are non-negative and the sum of lambda i's is 1. Now, this result is an extension of the definition of convex functions. So, if you recall that we say that f is convex if and only if f of lambda 1 x1 plus lambda 2 x2 less than or equal to lambda 1 f of x1 plus lambda 2 f of x2, where x1 and x2 belong to the set C and lambda 1 and lambda 2 are such that they are positive non-negative numbers and lambda 1 plus lambda 2 equal to 1. Now, instead of taking only 2 points, if we take any k points from the set C and take k lambdas which are non-negative such that their lambda is their sum is 1, then Jensens inequality says that a function is convex if and only if this inequality holds. Now, interestingly, this inequality also can be used to derive some other inequalities like arithmetic geometric mean inequality. We will see that later, but the result is very important, and it is useful in deriving other inequalities like AMG inequality or Yolder inequality. Now, let us try to prove this theorem. Now, the proof of this theorem is by method of mathematical induction, and it goes in 2 parts. So, now the first part assumes that f is convex and then this inequality holds. The other part assumes that this inequality holds and then shows that the f is convex. Now, let us prove this inequality by the principle of mathematical induction on k. Now, when k is equal to 2, the inequality holds, because by the definition of convex function. So, f is convex, then certainly if k is equal to 2, this inequality holds. So, for k equal to 2, the inequality holds for a convex function. Now, what we do is that we assume that the inequality holds for k minus 1 and then show that it also holds for the case k. So, let us assume that k is greater than 2 and the Jensens inequality holds for any collection of k minus 1 points in the set C. Now, let us add the kth point. So, suppose we have x1 to xk minus 1 were the initial points and we have added the point xk, and that then we take a convex combination of those k points. So, the sigma lambda I xi, where lambda i's are non-negative and sigma lambda I going from 1 to k is 1, that is the convex combination of these points. So, we are interested in finding out what happens at this. Now, we know that the inequality holds for 2 as well as k minus 1 points. So, let us make use of those facts. So, let us try to separate the first k minus 1 points from the kth point. So, let us take lambdas related to the first k minus 1 points, sum them up, let us call it as delta, and when delta is added to lambda k, we get 1. Right. So, we have now the first k minus 1 point, the combination of first k minus 1 point as 1 point and the kth point as the another point, and we have a convex combination of these two. So, f of lambda 1 x1 plus lambda 2 x2 up to lambda k xk, it can be written as, now what we have done is that we have separated the first k minus 1 point from the kth point. So, this the quantity in the inner parenthesis gives us the combination, linear combination of the first k minus 1 points, and then delta into that quantity plus lambda k x k. Note that delta plus lambda k is equal to 1. Okay, so, now we have 2 points in the domain and the convex combination of these 2 points. Now, you will see that by the definition of convex functions, we can write f of this is less than or equal to delta into f of the first point plus lambda k into f of x k. So, we were able to get lambda k f of x k out of this argument of f. Now, we also know that the inequality holds for k minus 1 points. Now, we have this k minus 1 points. So, since f is convex and the Jensens inequality holds for k minus 1 points, we can expand this and write it further as, so f of this quantity is less than or equal to lambda 1 by delta f of x 1 plus so on up to lambda k minus 1 by delta into f of x k minus 1. And now, when we simplify, what we get is lambda 1 f of x 1 plus lambda 2 f of x 2 up to lambda k f of x k. So, this implies that the Jensens inequality holds for k if f is a convex function. Now, the converse of now the other part of this theorem, that if this inequality holds, then we have to show that the f is convex. That is very straightforward. We just take the first 2 points, the remaining lambda k is equal to remaining lambdas to 0, and then we can show that it is easy to prove from the definition of convex function that the function is convex. So, the converse or the other part of the theorem is easy to prove. So, in the next class, we will study how to prove arithmetic geometric mean inequality using Jensens inequality. Also, we will study some of the properties of convex functions and how they can be used to derive more convex functions. So, if you recall, if we take a function f from a convex set to a set of real numbers, then according to Jensens inequality, f is convex if and only if this inequality holds where x1 and x1 to xk belong to the set C, lambda i's are non-negative and sigma lambda equal to 1. So, under these conditions that lambda I not non-negative and sigma lambda equal to 1, sigma lambda I xi is called a convex combinations of xi's. So, this inequality as you can see, it is a generalization of the definition of convex functions to more than 2 points in the convex sets. And in the last class, we proved this inequality, and I also mentioned that this inequality can also be used to derive many other inequalities like AMGM inequality or Holder inequality. So, today we will first see how to derive the AMGM, the arithmetic mean geometric mean inequality using Jensens inequality. So, now for that purpose, let us consider a convex function with, from set of positive numbers to the set of real numbers to be f x equal to minus log x. So, remember that this function is defined on the set C of which contains the set of positive real numbers. Now, let us apply Jensens inequality to this function. So, let us consider x1 to xk to be the k points in the set C, and let us assign lambda to be 1 by k to all the points. And then if we apply Jensens inequality, what we get is that minus log of sigma lambda xi is less than or equal to minus 1 by k sigma I going from 1 to k log of xi. Now, if we simplify, so what we get is log of the x1 plus x2 plus up to xk by k is greater than or equal to 1 by k log of x1 x2, x1 into x2 into x3 and so on up to xk. If we further simplify this, what we get is the arithmetic mean on the left side and then the geometric mean of those k numbers x1 to xk on the right side, and this clearly says that arithmetic mean of those k numbers is greater than or equal to geometric mean of those k numbers. So, this is an interesting way of proving arithmetic geometric mean inequality using Jensens inequality and using the fact that the function minus log x is a convex function. Now, we will look at some of the operations that preserve convexity of a function. So, the first property is that if you have a function from Rn to R, which is a convex function, and if we take any alpha which is a positive number, then alpha f is a convex function. So, most of these properties are easy to derive from the first principles. So, we have f is a convex function. So, if we take any x1 x2 in Rn and take a lambda in the closed interval 0 to 1, then by the definition of convexity, f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Now, if alpha is a positive number, we can multiply by alpha on both the sides, and then the inequality does not change the direction, and therefore, by multiplying alpha we get that alpha f also is a convex function. Now, here is another result which considers k convex functions from Rn to R, f1 to fk are those convex functions, and let us define a function f of x to be a non-negative or strictly positive combinations of those functions. So, f of x is nothing but sigma I going from 1 to k alpha I f I x, where each f I x is a convex function and alpha i's are strictly positive. Then the claim is that f is a convex function. Now, to prove this result, what we do is that we will first take only two functions, say f1 and f2, and prove the result, and then the extension to this general cases will be very obvious. So, let us consider two functions f1 and f2, and let f of x be f1 x plus f2 x. So, in this case we have assumed that alpha 1 is 1 and alpha 2 is 1, and then by using the convexity of each of those functions, we can say that for any x1 x2 in Rn and lambda in the closed interval 0 to 1, these two inequalities hold because of the convexity of the two functions. Now, if we add the left sides and add the right sides, what we get is that f1 plus f2 of lambda x1 plus 1 minus lambda x2 is less than or equal to the addition of these two, and that clearly shows that f1 plus f2 is a convex function. Now, this result can be extended to prove that f of x is a convex function, because if you multiply this by alpha 1 and alpha 2, the result holds, and similarly one can extend it to the general case of k different convex functions. So, these are some ways to get new convex functions from the existing convex functions. So, suppose we have a function f of x to be x square plus e to the power x. Now, you will see that this is x square is a convex function, e to the power x is a convex function. So, we are taking the sum of these two convex functions. So, that will be a convex function. Now, let us look at another result related to convexity of functions. So, let us consider a function h from R to R and f from R to R. So, both are real valued functions on the domain of real variables. And let us consider the composition of these two functions. So, let us call it as psi x, which is nothing but h of f of x. Now, the question is that under what conditions is psi x convex? Now, we know that for such real valued functions, remember that psi x is also a real valued function on the space of on the domain of real numbers. So, we have already seen the result that the function is convex if its second real valued function defined on the domain of real numbers is convex if its second derivative is non-negative. So, we can use that fact. Now, for that purpose what we need is that we need the twice differentiability of h and f. So, let us assume that f and h are twice differentiable, and we need to find the conditions under which the second derivative of psi x is non-negative. Now, if you write the second derivative of psi x, so you will get an expression something like this, which is shown here. Now, under what conditions psi 2 dash x is non-negative? Now, let us look at the first term. So, the f dash x square is a non-negative quantity. So, we want h 2 dash f x to be also non-negative. Now, let us look at the second quantity. Now, f 2 dash x and h dash f x, this product has to be non-negative. So, if that happens and h 2 dash f x is greater than or equal to 0, then we have psi 2 dash x greater than or equal to 0. Now, when will this will be greater than 0? So, in one case, suppose let us assume that f is convex. So, that means f 2 dash x is always greater than or equal to 0. Now, we have to make sure that h dash f x is greater than or equal to 0 and h 2 dash f x is greater than or equal to 0. Now, let us assume that h is also convex. So, if h is convex, then h 2 dash of f x is always greater than or equal to 0. So, the first quantity becomes non-negative, and suppose that h dash f x is also greater than or equal to 0. So, which means that the function is non-decreasing. So, if f is convex and the function h is convex and non-decreasing, then h of f x, which is nothing but psi x, becomes a convex function. So, psi is convex if h is convex and non-decreasing and f is convex. Now, if we look at so, let us consider the function f x is f x is a, so let f x be a convex function. So, let us consider any convex function and then psi x to be e to the power f x. Now, you will see that e to the power f of x. So, e of y is some function which is a convex function and non-decreasing function. So, this is this e function is nothing but the h function in our definition, and then we have f, which is a convex function. So, psi x equal to e to the power f x is a convex function. Because e is a convex function and non-decreasing convex function, and that composed with f of x, which is a convex function, will give us e to the power f x to be a convex function. Now, similarly, one can derive the condition that if h is convex and non-increasing, so h is convex means it is greater than or equal to 0, this quantity of course is greater than or equal to 0, and non-increasing means h dash f x is less than or equal to 0, then we want f2 dash x to be less than or equal to 0, right, and that will happen when f is concave. So, when f is and h is convex and non increasing, then psi 2 dash x is greater than or equal to 0 and psi is a convex function. Now, similar results can be derived for concave functions. Only thing in that case is that we have to find out the conditions under which psi 2 dash x is less than or equal to 0. So, one can use the same logic to derive those conditions. Now, let us see one theorem related to the convex functions and convex set. Remember that this theorem is not related to a convex programming problem, but in this case we are trying to maximize the convex functions over a compact set. So, let us see which is subset of R n be a compact convex set, and let f be a convex function defined from C to R. Then the claim is that the maximum of f occurs at a boundary point of C. So, in other words, the maximum of f, if we are trying to maximize a convex function over a compact convex set, then the maximum would occur at a boundary point. Now, let us prove by contradiction. So, suppose that the maximum exists at a point x star which is in the interior of the set. That is, we have f of x star greater than or equal to f of x for all x in C. Remember that x star is also in the set C and x star is in the interior of the set C. And then in such a case, let us see what happens. Now, the compactness of the set C is very important in this case, and let us try to utilize that. So, let us draw a line cutting through x star and cutting the boundary of C at x1 and x2. Now, remember that we have a compact convex set. So, this is our compact convex set C, and then suppose that x star is a point which is in the interior. Now, what we are doing is that we are trying to find a line passing through x star and which cuts the set C at some boundary points, say x1 and x2. Now, these boundary points do exist because we have assumed that C is a close bounded convex set. So, we can always find these points x1 and x2 where that line passing through x star cuts the boundary of this. And what we will prove is that if the maximum is at x star which is in the interior of the set C, then we can show that there will be points which are on the boundary which will have a function value higher than f of x star. So, that means that our claim that f of x star is the maximum or x star is the maximum point and f of x star is the maximum function value over the compact set C is not correct, and this claim will be derived based on the fact that f is a convex function. So, let us look at the proof of this. So, let us take a line segment through x star which is cutting the boundary of C at x1 x2. Now, we can write x star as a convex combinations of x1 and x2. So, we can write x star as lambda x1 plus 1 minus lambda x2 for some lambda in the open interval 0 to 1. So, remember that x star is not equal to x1 and x star is also not equal to x2 because it is a point on the in the interior of the set C. Now, we will use the convexity of the function f. So, since f is convex, we can write f of x star is nothing but that is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Now, let us consider the case where f of x1 is less than f of x2. Now, f of x1 less than f of x2, that means that f of x star is less than f of x2. So, which means that x star is not a global maximum, because we have found a point x2 on the boundary of the set C which has a function value higher than f of x star. So, which means that x star is not a global maximum. Now, similarly, we can consider the case where f of x1 is greater than f of x2. So, then obviously f of x star will be less than f of x1, and which again means that x star is not a global maximum. And if we consider the third case where f of x1 equal to f of x2, so which means that f of x star is less than or equal to f of x1 and f of x1 is nothing but f of x2. So, there are two possibilities that this inequality is strict inequality. So, in that case f of x star will be less than f of x1. So, which again is a contradiction that x star is a global maximum. So, the only thing which is possible is that f of x star equal to f of x1 equal to f of x2. So, that means that the function f is such that the value of the function at x star is same as the value of the function at x1 and same as the value of the function at x2. So, in that case certainly we have found a point on the boundary which is a maximum, but if the inequality holds, the strict inequality holds, then x star is not a global maximum. So, therefore, the maximum of a convex function over a compact convex set occurs at a boundary point. So, with this we complete our discussion on convex functions.